Wishing a nice day to everybody who are gathered here today. I am TMD Thilakarathne and here to present the research on plane strain modeling of embankment resting on soft soil stabilized with gravel compaction piles. This is the table of content, and here we are going to discuss about these topics. So I will be discussing it in the coming slides in detail. Moving on to the introduction, as you all know, most of the highway development projects in this country are done along the coastal belt of Sri Lanka, and most of these areas are having highly organic peaty soils, which are having less strength, and also the settlement is very excessive. So before doing any of these constructions, it is very important that we improve the ground. So we can use various methods to do this. Out of all those methods, gravel compaction piles is important. So preloading with GCPs is very common method that we use to improve compressible and weak soils. GCPs are providing two main actions. The first one is it will create shorter drainage paths, and then it will accelerate the radial consolidation, which will speed up the settlement. And the second one is the reinforcement action that will enhance the strength of the soil. So you can see an embankment resting on peaty soil, soft soil, which is stabilized with GCPs. Here you can see radial drainage happens around the GCP. So, so many past research have been done to study the behavior of GCP improved ground, but it is very complex in nature because various factors like shear strength of the GCP and the soil, soft soil properties will depend on this, depend on the behavior of GCP improved soft ground. Therefore, it is very much important to have a very clear idea about this. So most of these solutions are also based on unit cell analysis. And also in embankment construction, the embankments are constructed in as multi-stage construction. So this will further make this situation complex. Therefore, it is very much important that we have a sufficiently accurate finite element analysis to study the settlement variation, the pore pressure variation, how the stresses are going to vary in GCP improved soft ground. Here you can see in past studies done by past researchers, they have developed various different numerical analysis models, as you can see here. So if we are talking about this research, the scope of this research is to model an embankment section stabilized with GCPs as a plane strain, including smear effects. So for this study, we have selected an embankment section in the outer circular highway construction project in Sri Lanka, and settlement monitoring data which was obtained during the construction of the highway project is compared with our 1D finite element model simulation. And this numerical simulation was carried out using axisymmetric to plane strain approach, where the GCPs were converted into equivalent walls. So when discussing about axisymmetric to plane strain modeling, the 3D ground variation with GCPs is first converted it into a 2D model with equivalent properties. For this, we have used the method proposed by Tan et al. 2008. So according to him, a system of GCPs arranged in a square grid, the equivalent plane strain parameters can be expressed as in this figure. So you can see axisymmetric unit cell is converted to plane strain by using his method. So to derive these parameters, we have used this set of equations. You can see the notations here, what it means. From BC to KV, we have explained all this. So these are the notations that we used. And the reference case is we have selected an embankment section at Karavalapiti interchange, ramp F of the outer circular highway. This is 7 meter high, 17 meter wide embankment with a slope of 1:2. And this embankment is founded on a 15 meter thick soft peat clay, and the groundwater table is in the ground surface. The water table is in the ground level. And the GCPs of this case are 0.3 meter diameter, and it is arranged in square pattern with spacing 1.5 to 1.3. meters. And the reference problem was considered as a plane strain 2-dimensional consolidation at this section F0 plus 560 meters change, and a finite element package Plaxis 2D was used for this study. Here you can see the cross-section of the GCP supported embankment at the chain edge FK0 plus 560. So these are the boundary conditions. The bedrock was considered as the bottom boundary, rigid and impermeable. The vertical boundaries were allowed movement in vertical direction, and the horizontal displacement was fixed as you can see in figure 5. And the drainage boundary was taken at the ground level, while the lateral boundaries were set impervious and closed. So these are the material model and material parameters that we use. So table 1 and table 2 shows all the parameters that we took from the laboratory test data. And we did some assumptions, like we took details from some studies. That is, we got the ratio between RS and RC to be 2, that is based on the research of Bergado and Thilakarathne, and also the average value of KH divided by KV as 1.63 for undisturbed soil, and KH divided by KV of 1 for the smear zone was selected for this study. And this is the mesh generation. So as you all can see in this figure, a 15-node triangular elements were used here. Fine meshing was adapted to provide accurate results of the settlement, stresses, and pore water pressure. And also we used the ramp. Here you can see in table 4, the construction stages of the ramp F. So we used the real construction procedure for to do this study, and also the parameters and the surcharge period was updated using the back calculated strength parameters. So moving on to the results and discussions, we did this. We ran our simulation for 3 conditions: settlement plate A, B, and C. So it is for left, center, and the right. So you can see in red color are the field measurements that we got, and green color we have FEM without smear and with smear. So you can see the results are accurate enough, and they are matching very well with the field measurements. The maximum settlement recorded in the left and right side of the embankment was 0.426 meters and 1.256 meters respectively. And here you can see a differential settlement has occurred in that section. The main reason for this is the left side of the embankment was already filled with a 10-meter high soil stockpile before the construction started. This has improved the soil on the left side and caused the differential settlement. So here this figure shows how the embankment loading is carried by GCPs and the surrounding soil. You can see it in figure 6, the effective stress distribution due to embankment loading. And here we have used various SCF. You can see variation of SCF at different MSL, but for this study, we used a SCF value of 3, but it is observed that it ranges between 2 to 3.5. So as you can see here with the depth for left, center, and right sides of the embankment, average stress concentration factors varies like this. And when moving to the excess pore water pressure variation with and without smear at a depth of 6 meters, here you can see it in figure number 8. The predicted maximum excess pore water pressure was less than 25 kilopascals, which shows the dissipation of excess pore water pressure is very fast due to the GCP installation. And also the important fact is, although there is no much variation in settlement with the smear effects, the variation of excess pore water pressure can be seen clearly, as in figure 8. So when moving on to the conclusion, there are 2 main basic conclusions. The first one is the model of the GCP stabilized embankment foundation yielded acceptable results in terms of settlement variation. And the second one is, it is also very important that the stiffness of the material and area replacement ratio are significantly important in predicting the behavior of GCP stabilized ground. These are the references. Thank you.